Hey guys, Jake here, coming at you with some more math today. Here's what we're going to be going over today, how to find horizontal asymptotes in rational functions. And I'm going to be showing you how to do it with this function right here. So let's go ahead and jump into it. When you're trying to find a horizontal asymptote of a rational function, all you really are essentially doing is figuring out what y value this function is approaching as x goes to infinity. So essentially all that means is we just need to take our function and take the limit as x goes to infinity of that function. And basically that tells us, if we imagine some function on a graph, we have some horizontal asymptote, what y value is this function getting really, really close to as x gets infinitely big and we just go off infinitely in this direction. And whatever that y value is exactly where our horizontal asymptote would be. So this is all we're doing in this case. So the first thing we really want to do with this is kind of expand everything out and get it in a form where it actually looks like a rational function. Because if we look at our denominator here, it doesn't, it's not in the form that it really looks like a polynomial. So what we want to do is FOIL this out so that we kind of multiply out all these parentheses here, FOIL that out so that we have an expanded, sum or difference of a bunch of terms that are made up of a constant times x to some power. So let's go ahead and do that first. So we'll have the first terms times each other. So x squared times 3x squared would give us 3x to the fourth. X squared times negative x would give us negative x cubed. 1 times 3x squared would give us plus 3x squared. And then 1 times negative x would give us minus x. Okay, so now we've expanded it all out. And you can see more clearly that we have a polynomial on the bottom and the top giving us a rational function. So now, when we're evaluating this limit as x goes to infinity, all we need to do is imagine multiplying both the top and the bottom of this fraction by 1 over the highest powered x term that we have in our denominator. So since the bottom of the fraction, the highest power x we have is x to the fourth, we're going to multiply both the top and the bottom by 1 over x to the fourth. Because if we multiply the top and the bottom of a fraction by the same thing, it doesn't change its value. So this is going to be equivalent here. So now we just need to take this 1 over x to the fourth and distribute it to each term on the top and each term on the bottom. Doing that would give us something like this. 6x to the fourth over x to the fourth minus 7 over x to the fourth all over 3x to the fourth over x to the fourth minus x cubed over x to the fourth plus 3x squared over x to the fourth minus x over x to the fourth. Right, so essentially all this does is it puts every single term in the top and the bottom of our fraction and just puts it over x to the fourth. So now what we want to do is simplify each of these terms because, most of these have an x on the top and the bottom within just each little term, so we can cancel some of those out. So let's go ahead and do that. And when I do it, I'll write them up at the top of the board here. So this here, we have x to the fourth on the top and the bottom. Those are just going to cancel. So we're just going to have limit as x goes to infinity of 6. Nothing will simplify here because we have no x's on the top. So we'll just get minus 7 over x to the fourth over x to the fourth will cancel x to the fourth on the top and bottom. So we'll just have 3. We have 3 x's on the top, which will cancel with 3 of the x's on the bottom, leaving us with just 1 over x, so minus 1 over x. We have 2 x's on the top, which will cancel with 2 of our x's on the bottom, leaving us with 3 over x squared. And then over here, we have 1x on the top, which will cancel with 1 of those x's, leaving us with 3 x's on the bottom. So we'll have minus 1 over x cubed. So now that it's completely simplified, what we want to do is think about our limit properties. A couple of those limit properties say that if we have the limit of a fraction as long as taking the limit of just the bottom of our fraction doesn't give us 0, we can kind of split this up. So this would be the same as, instead of taking the limit of that whole fraction, we could take the limit as x goes to infinity of the top and put it over the limit as x goes to infinity of the bottom. So this is actually going to be equivalent to just taking the limit of the whole fraction. We could, confirm that this limit on the bottom doesn't give us 0, but we'll see in a second that it doesn't. Another one of the limit properties says that if we have the limit of a bunch of terms being added or subtracted together, we can instead take the limit of each individual term and then add or subtract all those limits together and end up with the same value. So what that tells us is we could take this, and instead of taking each of these, kind of longer limits separately, we can say this is actually equivalent to the limit as x goes to infinity of 6 minus the limit as x goes to infinity of 7 over x to the 4th, all over the limit as x goes to infinity of 3 minus the limit as x goes to infinity of 1 over x, and so on. Okay, so now we've essentially broken this big nasty limit up into 6 really small, much easier limits. And what we want to think about is, let's first consider these ones here. This limit, this limit, this limit, and this limit. And the reason why is, notice each of these 4 limits that I've circled, all of them have the limit as x goes to infinity of some constant divided by x to some power. So think about all 4 of these limits as x gets infinitely large, as x goes to infinity. If we're taking a constant divided by a denominator that just keeps on getting bigger and bigger, that fraction as a whole is going to go towards 0. Because in all these cases, our denominator is just going to get infinitely large, and we're just going to end up with some constant divided by a bigger and bigger and bigger and bigger number. Now, if you actually do that on a calculator, divide 7 by 1,000,000, and then 10 million, and then 100 million, and keep doing that, you're going to see that your result gets a smaller and smaller decimal, or a smaller and smaller fraction, which just puts us closer and closer to 0. So basically, all we end up with is a limit as x goes to infinity of a constant minus 0, all over the limit as x goes to infinity of another constant plus or minus a bunch of zeros. So these 4 limits over here don't actually contribute anything. So all we end up with is the limit as x goes to infinity of 6, which, based on our first limit property, if we have the limit of a constant, it's just going to be that constant. And then same thing here, the limit of a constant is just that constant. So we just have 6 over 3, which is 2. So that tells us that we have a horizontal asymptote at y equals 2, because this limit as x goes to infinity is 2. Now click on this link I have on the screen here, the playlist full of other videos of limits of x going to infinity. A bunch of other videos on the same topic should help you kind of keep things rolling here and really learn this stuff. So click on that real quick, go check those out, and hope it helps.